In this video, we'll be looking at the relationship between potential energy and work. The video is split into two parts. In the first part, we'll look at the definitions, and I will also derive the formula for the gravitational potential energy near Earth's surface. And in the second part of the video, we'll be looking at the relationship between the potential energy and the work for two different cases. So we're already familiar with kinetic energy. We know that that's the energy associated with the motion of an object. So it's a real energy. It's something tangible. The definition of the potential energy is a little harder, and this is the best one that I've found. So it's the energy that exists in a body as a result of its position or condition, rather than of its motion. So it's something like the stored energy of the object. You can consider that it's the stored energy of an object, but we can only convert it to real energy, so to kinetic energy, for example, if we know the right conditions to apply to that object. And there are, because of the way energy can be stored, there's a number of different types of potential energy. So we have the gravitational potential energy, which is the one that we will be most commonly dealing with. We have the chemical potential energy. So for example, fuel or petrol contains chemical potential energy, and we can release that energy for our use if we apply the right conditions to the fuel. So if we get the fuel up to the right temperature. And a third type of potential energy is the elastic potential energy, which is the energy stored in a spring. The relationship between work and potential energy is very similar to that between work and kinetic energy, except the opposite. So the work is equal to negative of the change of the potential energy. So in the next slide, I'm going to derive an expression for the gravitational potential energy near the Earth's surface. And so the expression itself, or the formula itself, is very simple, but the sign on the formula is, or at least appears to, contradict everything that we've learned so far. So for that reason, I'm going to derive it from nearly first principles. The general definition of gravitational potential energy should come as no surprise. So in order to be able to derive the gravitational potential energy, we need a definition that we can use to convert into a mathematical equation. So we need a slightly more specific definition. And for that purpose, gravitational potential energy is defined as the work done, or the work required, to move an object from its current position in the gravitational field to a position where there's zero gravitational potential energy. So if we have a look at an object on our Earth, we know that our Earth has a gravitational field, and from the first video in this topic on the four forces, we know that gravity is the one force which extends to infinity. So in order to remove an object from the gravitational field on Earth, we need to move it an infinite distance away. So for this investigation, I'm going to look at an apple that's sitting at some height above Earth. So to find an expression for the gravitational potential energy, we have to take that apple and we move it a distance of infinity away. So because I'm now looking at a difference, I'm looking at the difference in my gravitational potential energy between where the apple was sitting on Earth and infinity, I can choose my 0 point. So I'm going to choose that the radius of Earth, or the surface of Earth, is my 0 point. So if an object is sitting on the surface of the Earth, its displacement is 0. And we're going to derive the gravitational potential energy for an object at some height h, very near the surface of the Earth. And so as always, we'll start with what we know. We know that the force due to gravity varies with its distance r. So it's a variable force, varying with the displacement of the object from Earth. And we also know that the integral of the force due to gravity as a function of the displacement gives us a term or an equation for the gravitational potential energy as a function of that distance. So these 2 points, at the moment we haven't learnt them. We'll look at them in more detail in the topic on gravitation. And so for now, I'll just ask that you take that these are true. So to find an expression for the GPE, we're looking for the work. And we know that we can calculate the work done by a variable force by integrating the force as a function of the distance over the distance of interest. So in this case, the work done by gravity on the apple is equal to the integral of the force due to gravity, dr, from its initial position, h, to infinity, to the final position. We also know then, from point 2, that the integral of the force dr is then equal to some expression for the gravitational potential energy, at that point R. So we analyse that expression for the gravitational potential energy between h and infinity, and we find that the work done is equal to negative of the GPE at that height. So we have a general expression for the work done by gravity. In our specific situation, we're looking at an apple that is near to Earth's surface. And near to Earth's surface, we assume that the gravitational force is constant. And we've done that for this whole course. So that is, we assume the acceleration due to gravity is equal to negative 9.8 meters per second squared. So 9.8 meters per second squared towards the Earth's surface. And we know that when we have a constant force, then we can calculate the work done by the constant force as the dot product of that force and the displacement. So in the case of our apple, the force acting is the force due to gravity, and the displacement is the height above the Earth. Because the force is vertical and the height, or the displacement, is vertical, then the work due to gravity is just equal to Fg times h, which is equal to mgh, and g is negative. So we find that in the specific case of an object near the Earth's surface, the work done to raise it height h is equal to negative mgh. So now we have two expressions for the work done on the apple, and if we combine those two expressions, we find that the gravitational potential energy of an object at some height h near Earth's surface is equal to mgh. And the key point here to remember, even if you forget the rest of the derivation, is that because of the way the gravitational potential energy is defined, it's a positive value. So that means that in this formula, when we're talking about the gravitational potential of an object near Earth's surface, the g is greater than 0. And this is the apparent contradiction I was talking about. So up until now, we've said that g is negative. And in this case, g is still negative, but because of the way the gravitational potential energy is defined, in the formula for gravitational potential energy, we take that the g is positive.